Right, let's get started on the next problem. So today we're going to be working on this one. This is number 572, subtree of another tree. Given the roots of two binary trees, root and subroot, return true if there is a subtree of root with the same structure and node values of subroot, and false otherwise. I see. So, I think this problem, from what I'm feeling right now, has two components. One is a traversal to find potential roots. And what I mean by that is that we need to find potential subroots, right? So starting at the root, we need to basically traverse through until we find a number that resembles that has the same value as the subroot, and then we can start from there to evaluate the left and right subtrees. That second part in that case is simply checking whether or not the tree rooted at this particular part is the same tree as the tree rooted at this subroot. So we're going to have to implement a same tree in this case. We'll call it subroot still. And we can take a recursive approach. So we can return is same tree. We can say root dot val is equal to subroot dot val, and is same tree root dot left subroot dot left, and is same tree root dot right subroot dot right. Root dot left is null, and subroot, or rather here, if root is null and the subroot is not null, or, and we have to wrap this in parentheses, so a little bit of optimization here. Root is not null and the subroot is null, return false. So that's sort of the basic stuff. If let's see, if root is null and subroot is null, return true. Because if they're both null, then there's no point in checking the left and right subroots. Root.val. Remember this sort of optimization. And subroot dot left is null, and root dot right is null. Subroot dot right is null. Return true. So if they have the same value and they have no children, then we just return true. Both of them have no children. And this is just an optimization, so we don't go an additional layer checking into our recursion tree. Otherwise, it's just a standard. We check our current root, we check our left, we check our right. So this is a pre-order traversal, I believe, where we start by evaluating our current node, then with our left, then our right. So pre-order in the sense that the node that we visit first is the node that we process first. Rather than in order, which would be we go all the way to the left, then the middle, then the right. Okay. So now we need to actually go and find the node. So two components. first find all plausible nodes that we can evaluate. Otherwise, or then check if the tree rooted at that point is the same. So now we need to do a traversal here. And I think in this case, we can just do if root.val, and we're going to have to wrap these in. These little backticks. I forgot about that. Sometimes Kotlin just do be like that. Is not the same as subroot.val. Actually, if it is the same, then check do we want to add all of the possible nodes into like a queue or into like a list, and then we just evaluate them at once? Has found same, or has found subtree. Actually, we can just say if is same tree root. Actually, no. Is same tree root subroot. Return true. So if we found it, then we just return true. Otherwise, we do is subtree root.left subroot, and is subtree root.right subroot. Otherwise, we return false. I'm just thinking now whether or not this would actually work, given that we're returning true here, we're returning false here, but we're really returning false. Let's see. Okay, so you start here. Not the same value. So we go left. Is the same value, we check. So root val here, same. Okay, check the left, same, no children. Check the right, same, no children. So this returns true. So this returns true here within this confine. Then it checks the right. Which which checks the left and the right, which are null. Which returns false. So now we have a return true and a return false. What we could do is this. We use an OR statement. So if one of these, so now if this is true, then we, assuming that the JVM does do the short circuiting, then this just automatically goes back up to the top here. Or this returns, right? Sorry. because this is not true. So it is subtree left and right. Then this on the left will return true, and therefore this returns true as a whole. Now in a case like this, we go here to the left, same tree, same tree, same tree, not same tree. This returns false. Then we go to the next one. And then this one is also false. But we do need a if root.left, or if root is null and subroot is not null, return false. And that can only be the case when we do the left and the right. So this is basically just a terminating condition for the bottom part, so we just don't go crazy there. I'm not too thrilled about this still, in the sense that I'm not very confident that this will work. But I think it makes sense. The problem then is that there may be, perhaps that there's a chance that there is a subroot within this tree. Like maybe 4, 1, 2 is actually here instead. So actually we don't want this to happen, because otherwise then it'll just return. Actually it won't. Yeah. Because then it won't do anything. So this wouldn't actually compile, I don't think. So if we encounter the same value, we check if this is the same tree. However, we still want to check the left and the right subtrees. So we want to basically double check to make sure that we don't have like a tree within here, like a 4, 1, 2 here, that we miss if that's the case. So we still need to check the left and the right subtrees in that case. Okay. If the left root is null and subroot is not null, or should we do an and? Yeah, we can worry about optimization later. I think this is actually what will work. Let's double check and let's see if, or let's give it a toss. Root dot C. Doesn't like that we have non-nullables there, and I think it's the same thing here. Yeah. Okay, cool. So it looks like it worked for that one. Let's toss in the other case. And let's see. Okay, that looks fine. Let's see if we can speed this up. The current runtime is 249 milliseconds on the test cases. What we could do is that we could introduce another case and say if root dot left is null and root.right is null, and the subroot is not null, we just return false. So we save an extra two calls here for childless nodes. Root.left is null, and subroot is not null. This might actually be redundant then. And root.right is null, and subroot is not null. Return false. And I think this actually does imply this, right? Yeah, because this is just checking both cases. So as long as one of the cases is, if the left is null or the right is null, no, that's not quite. And what I mean by that is that I think if we had a situation like this, and let's say that this 1 here didn't exist, and this 4 became a 4, 1, 2, then the left of here is not, or the left of here would be null, the right would be non-null. But since we have this case where the right, or where the left is null and the subroot is not null, we don't want to return false in that case, no. Okay, so I think this might be as far as we can go in terms of this sort of avoiding additional calls, but I could be wrong. Okay, cool. So looks like we shaved it down from 249 to 152 milliseconds, which is pretty good actually. That's actually quite good. Let's see. Is there anything else that we can reconsider here? No, I think we need to evaluate all of them. We need to evaluate the rest of the nodes, even if they aren't the same value, because we could have a subroot tree sort of buried underneath. So I think this is as far as we can actually go, but actually a very, very nice sort of binary tree problem that we're dealing with here, combining some of the elements that we've had from previous problems, like the pre-order traversal, with the same tree, right? We're checking first the node that we visit, then left and right. And then we also do a little bit of traversal on the is subtree part of it, basically to traverse to go find the node that we want. In this case, it really doesn't matter which one we use, pre-order, in-order, post-order, because we really realistically need to check all of the nodes in the tree in order to find a potential route, pretty much. Maybe there's some more additional optimizations that you can consider there, but I think this is as far as we can go realistically on, like, at least like on a very sort of basic level. And anything beyond this would be interesting to see, and it would probably help, but I'm not sure whether or not at that point whether we would be sacrificing sort of readability for efficiency. There's a trade-off there to argue about. In any case, let's try to submit and let's see if there are any issues, or if it works, then let's see our runtime. Okay, so it seems like it's a pretty average solution. Runtime percentile of 49.45%, so pretty much right in the middle. Memory usage of 39.56%, so a little bit more memory usage, but it's still fine. And I think this is honestly quite fine. Perhaps there's something else that we could add on to it, but I think honestly this is a good enough solution that runs in that seems like it runs in the asymptotic runtime, that would be sort of fine for an interview. Let's see. I guess the main bottleneck in this case is that if we had a bunch of nodes in our main tree that had the same value as our subtree, and they are the same tree, or maybe not even, maybe it's just a tree that doesn't exist within the sorry, within the subtree. So what I'm thinking is basically, imagine if these were all 4s, and this is 4, 1, 2, right? So we start here. It's the same value. We check left, right, or yeah, same value left, not true. We go back here, check the left, check here, not quite, check here, nothing on left and right, go back, right. So basically we'd have to check each time, so it's a little bit slow there. Maybe there's a solution to be thought of there. But I think with this runtime, I'm fine with it as it is. Maybe I'll go ahead and think about it a little bit more off camera, but I think I'm fine leaving it here. So, in any case, I hope you learned something, and I'll see you for the next problem.